Okay, so we have just discussions. If you prefer discussion or just review. Any questions so far? Any material this semester, especially the second half for our final exam. Oh, I just get contacted by Kakema. Kakema will contact you about the time, exact time for the another problem sessions, either on Saturday or Sunday. Just make appointment with him. Just agree on some time later on. I would suggest Saturday at 4 something, so to 5:30 or something. Or you can, otherwise you can find some other time. Okay, questions? If not, then let's go back to the material. Let me just get the 388. Beginning to the table of content. All right, so our midterm exam. So I don't think anyone in this class missed the midterm. So we don't have to review the first half of the material unless you need it, but uh, unlikely. We get to the application derivative. Let's see. Which material did we stop for the midterm exam? I think we stop here. Mean value. Yes, I think we stop here. Mean value. This is for the midterm. So this is for final. So from numerical integration to the application of integral. So that's that stigma thing. You see, how you call it? Riemann sum, left Riemann sum, right Riemann sum, upper Riemann, lower Riemann. What else? A parabolic method, and then no, parabolic is trapezoidal method. This method. Okay, those kind of stuff. And application of integrals, area, volume of revolutions, solids of revolutions. This one is not. Just integrations. That one. Solid there. Not. Oh, sorry. This should be in there. Work and fluid force. Moment center of mass. Not. So I better. There. Okay. And chapter 6. Log functions, inverse functions, natural exponential, or linear. Skip this one. There and there. Okay, so those are the material for our let me check. Did I think I made a mistake here. So our midterm Can you recall the our midterm exam up to, I think, nothing here. Sorry. I think mean value, but mean value for derivative, not mean value for integral. So I guess stop here. That's the midterm. But I'll find out. Let you know this coming days the uh, exact material. This is fine. Okay. Or let me check is there any? Okay. Let me find out. No announcement yet at this point. Okay, so I think this is our material. Start from antiderivative. I'll announce that if I was mistaken later. All right, so we start from here, antiderivative, differential equations. So this area, definite integral, first fundamental theorem calculus, second fundamental, there. Okay, so let's see, this is 3, this is 1, 2. Yeah, that's about it, about even. 3 chapters before and 3 chapters after the midterm exam. Okay. All right. Is there any material that you want me to review more precisely instead of going through all these things?
Sir, can you review chapter 5.5?
5. Work and fluid force. All right. We haven't talked about in detail about we talk about fluid, but not about about pumping things. We talk about the problems, but not on spring, like in the joint quiz. All right, so let's talk about it. What's 301? Okay, so work is force times distance. This is the fundamental things. Okay, so now if you have a the main idea is to do partitions like the okay. So application to springs. Top of this one, we skip this one before, but we go directly to the more longer part. Actually, the fluid force. All right. So what spring? You have Hooke's law in physics. You have the force of a exerted on a spring is proportional to the its stretch length. So x k times x. Okay. So if you have a string and then you pull the string, the extra length you get, this is what we call a delta x. So the force exerted on this length is k times not x, but actually delta x, the extra length. Okay, so that's the main idea. So if you have a natural spring, natural length of spring is 0.2. Okay, so this part, and it takes a force of 12 Newton to keep it extended 0.04, so 0.04 the extra length. Find work the stretching spring natural length to length. Okay, just so I don't have to write it down, but do some problems later. Okay, so what we do here. Okay, first of all, we found out the k. Okay, so what k? It takes force 12 Newton. Okay, so 12 is k times delta x. The delta is not this 0.2 meters because that's the length of the spring. That extended length that we need. Okay. So k is 12 divided by 4. That's 300. Okay. So we know the k. Okay. All right. So what's the problem here? Find the work done in stretching the spring from its natural length to a length of 0.3 meters. Okay, so the idea is let's see. Let's see. Zero spring here. That's a spring. And then it stretched to this one. Okay, and it looks like stretching. You partition this one. Okay, so you stretch this part, give you a force. Yes. Stretching this part give you k times x. This part, okay. So from moving this part, you have k times this x. Okay. Okay, so the whole thing, so the say delta omega is k times this. So the omega is, okay, let me write this down. Okay. Uh, spring. We have a spring. This is the natural length minus L. This is natural length. So it stretched out to this one. Stretch. Okay, so the question is, what was the force work done by the force? All right, so if you this extra length, you define here. Okay, so the x0, x1, x2, x3, which is xn, for example, equals say d. What we compute here is that, well, stretch this length. Well, when you stretch this length, you get delta y1 is k times x1. Okay. And what about delta 2? Stretch this length, right? 1 by 1. This is k times delta x2. Okay. So at the end, what you have is I, which is the sum of this. And but this is a Riemann sum. Riemann sum times the delta x, I think. Yes, it's delta x. So the W is, well, that is the from 0 to whatever b here. Okay, so this x and becomes x. Okay, so that's what you get here is k over, let's see, over 2. Yeah, x squared. So that looks like this one, the formula. Okay, k over 2 is this p squared. Yes. That's the idea of this working with the whispering. Okay, so this is what you get. So then let's do about pumping liquid in Joule. Okay. Sorry, let's see. Let's take a Let's do this problem here. Uh, like problem 13. You have a cylinder tank. Assume that the base of radius is 4, height 10. Tank is full of oil. Okay, so you have, let me just tank. Radius of base is 4. Okay, and the height is 10. So you're pumping the oil. This is containing oil. Pump this out. Here, the top of the tank. Okay, so that's problem 13. But now the problem 14, what I'll do is 14. Has a cross sections. So this not a cylinder anymore, but a 4 plus x above the base. So it's say this is x. Okay. So going up, this is the radius is bigger because 4 plus x. So it's here. Okay. At the height x, the radius is 4 plus x. Okay, so you need to pump the oil out from the top. So we compute the work done in pumping all the oil. Okay, so this is the setup, so we can. So, okay, let's do this one. Where is that thing? Okay. Let me have, let me write it down. Okay. At the height h, this is 10. Okay, and the radius, if you, this is height h, for example. So the letter match. Okay. So this radius here, radius at the height h is 4 plus, this is 4. Okay, is 10. So at the top, this is 4 times, this is 14. Okay, and you have a pump here. Okay, so how we formulate the problem? Okay, so let's say, okay, we take this part here. This is a sample. This is a sample. Okay, at height h. Okay, so that is delta h. Okay, and the radius is 4 plus h. We need to move this up to this one here. So the height 10 minus h. Okay, so what's it? So the volume sample work is gravitational force for this. 4 times distance. Gravitational force is based on the mass, right? So G times the mass. Mass is volumes times density. Okay. So this is just volumes times density. Okay, so what's the volume? Volume is, let's see. So there we go. This is 4 plus h. This is delta h. So this has volume is 4 pi r square times is the parentheses there. Okay, times density. Density here is, say, force density. Okay, force density is, say, delta. Okay, so what we have is delta times pi 4 plus h square delta h. Okay, times distance. What is distance? Distance is this one here. Yeah. So this is basically we have 10 minus h because this is h. Okay. So that is the delta work is times. Okay. So what about the work? Well, that is the sum of. Okay. And when you take this is Riemann sum. Times h. Okay. Take limit s because this is all polynomial. You can take limit. The integral exists. So we take limit. Limiting as partition goes to 0. Okay. So we get integral. Okay, from 0 to 10 actually. Okay, so 8. So let's go 8 from 0 to delta pi square. Okay, so can compute this one. 10. Can compute this. So that's how you formulate the problem in terms of integral. Then you can compute this because this is a polynomial. In this delta pi. What is this? It's a little bit. So that's 16 plus. Let's see what is 8. 8 plus. Okay, so what we have here? 160. H you get negative 16. You get 10. So minus 6, 8. And then you get minus 8, you get 10. There we go. 16, 8, 10. Yeah. So you get 160 minus 6, 3 8 square plus 2/3 8 cube 0 10. And the bound's easy because you plug in h 0, everything's 0, plug in 10, and so 160 1600 minus 300 plus 2/3, so 667. There we go. Something like that. Okay. Questions? All right. Well, it's 8:55. Okay. I guess other problem you can ask whether during the problem session with the CalCamel later, or you can ask me in using the chat in Teams. Okay, I guess I'll stop sharing. I'll stop the record now.